Okay, let's come to the examples later. Let's just discuss the types of critical points first. So critical points are classified into 3 points. So first is your local maxima, then you have local minima, and then there's a point called saddle point. Saddle point. So your local maxima is where your function's derivative. The local maxima looks like this, where this thing is called your local maxima. This where it goes is called the local minima, and a saddle point is somewhere where it's what happens in a local maxima is a point where before that point the function is increasing and then it starts decreasing after that. And local minima, it goes like first you have a decreasing function till that point, and then after that point the function starts increasing. But in a saddle point, you either have the function increasing after before and after the saddle point, or it's simply the saddle point is where, when we classify it in this manner, let's just do it in terms of f dash. So for a local maxima, at just give me a minute. Yeah. So we were discussing local maxima, local minima, and saddle points. So local maxima is the point as we were discussing where, let's say, if we are taking x naught and then classifying it as these 3 points, then x naught is the local maxima if there's one interval. This is a complicated, in terms of definition, it's complicated, but when you look at a graph, it's very easy to look at it that it's, if this is x naught, then you need an interval around it. Let's just call it x naught minus something. You can call it anything. Epsilon and x naught plus epsilon, where from in this interval x naught minus epsilon, so x naught is x naught and your function is fx. If your function is fx and a point x naught is a point such that your f dash x naught is 0, then this x naught is classified in these 3 categories. If in x naught minus epsilon, your f dash, let me just call this point x, where your x belongs to f dash x is, so if it's like this, then your f dash x should be greater than 0. This should be greater than 0 for this interval. Or you can say that your f dash x should be greater than 0 for x belonging to x naught minus epsilon to x naught, right? So in this interval, your f dash x should be greater than 0. Whenever your f dash x is greater than 0, that means the function goes up. It's an increasing function, right? So we want that till this point x naught. So from x naught minus epsilon to x naught, your function should be increasing. That means your f dash x should be greater than 0 and your f dash x should be less than 0 for x belonging to x naught to x naught plus epsilon, right? And the opposite goes here. So f dash x, so here we say that you should get an interval x naught minus x naught minus epsilon, x naught plus epsilon. And x by this x naught minus epsilon, x naught plus epsilon, we mean that we just need an interval around x naught. So if x naught is a point, we need an interval around it such that in this part of that interval, so we're calling this point to be x naught minus epsilon. Why minus epsilon? Because obviously this point, whatever this point is going to be lying on the left side of x naught, right? So that's why we're subtracting something. We don't know what that something is, so we're calling it epsilon. So in this part, it should be increasing, and in this part, it should be decreasing for this point to be a local max, right? And the opposite goes for local minima. So this should be less than 0 for this same thing. The same thing copied here. And your f dash x should be greater than 0 for the same thing copied here. And if your point is not a local maxima and not a local minima, then it's a saddle point. Is this part clear? This is the distinction between local maxima, local minima, and saddle points. Let's do a question. And how do we identify these things? The first way is by looking at the patterns. That's one way to do it. And then other, which is not, uh, it's not a very, uh, it's not something that you are advised to use. So you don't use it. Instead, you can use the second derivative test. So your second derivative test is to identify which one of the critical points is the given point. So let's say you have f. Yeah. So in your double derivative test, it's the double derivative test for local maxima and local minima. So let's say you have a point x naught where your f dash x naught is 0, right? Now you want to identify if this point is a local maxima and local minima. And you obviously can't go by the definition of local maxima and minima because for that you will have to check for literally every point in this interval and every point in this interval, which is this should be for all x, and this is also for all x. So a simpler way to do this thing is that you check the double derivative. If your double derivative at x naught is greater than 0, then it's a point of local minima. So this implies that x naught is local minima. And if your f dash this double derivative x naught is less than 0, that means your x naught is a local maximum.
So, ma'am, you mean to say that double derivative test is the better option to check for local minima and maxima?
Yeah, that's how you check local maxima and minima. Otherwise, if you go by the very definition of this, if you do it this way, then it's unless you have a very obvious function. Let's say your derivative is if your derivative comes out to be this 2x and minus 2x. If it comes out something like this, then you know that it's for x less than 0, x greater than 0. If this is your derivative, then we know that this derivative is increasing after before 0 and decreasing. So if this is 0, that means what I'm trying to say here is the derivative is this one is greater than 0 for x belonging to 0 or for minus epsilon and 0, right? So for minus epsilon and 0 in this interval, if this is minus epsilon and 0 interval, then this thing and if this is your derivative of some function, say, then we clearly know that this is greater than 0 after in this interval 0 to epsilon, and in minus epsilon to 0 it's a decreasing function, right? So we know that this is going to be true. So that way you can figure out that it's a local maxima or minima in this particular function, but otherwise you can't go by the very definition of local maxima and minima.
Okay, ma'am.
because you'll have to check for every point, and not every derivative is that simple
Ma'am,
to
how we are
identify.
check, ma'am, how we have to check for every point? We just have to check like just a point before that derivative is zero, like minus epsilon and just one plus epsilon, 2 points, na ma'am? If you're going by
No,
that
no, not two
definition.
points. This definition says if your f dash, if this is if this is your function, and if this is your local maxima point, then you have to check for every point. So at every point, the derivative should be positive here. So in this, that means you need an interval. If this is your point x naught, then you need an interval from something left to the point x naught till the point x naught. You need some interval here where your function is increasing. That means for every point, you would need f dash x to be greater than 0. So for every point, you need this. That's why I've written for all. Here also it's for all. That means you'll have to check for every point in this interval and in this interval.
Just a point just before that also, it may be possible that it would be positive and the other point would be negative. So in a way, we can say that it's a local minim, like local maxima. Just 1 point before and 1 point after that.
You can't you can't decide by one point. Not all functions are that simple. That's what I just discussed. If you have a derivative, if you have derivative in such a sense, if your derivative comes out to be, let's say, I don't want to take 2x, but let's say if it's 2x, and then now we know that this is obviously always going to be greater than 0 when you take x greater than 0. And when you will take x less than 0, this will obviously be less than 0. So here the function is very obvious, but not every derivative is that obvious. Every function that you're going to find would not be that obvious.
Can you give example where it's not so obvious so that it's more clear to us?
I have to think of one right now. I can't think of any. You can go by functions. Let's say your derivative turns out to be something like this, where you can't decide if it's, you have a lot of polynomials too, where you can't actually decide because you don't know where the roots are, right? When you discuss polynomials, then till a certain degree you can identify the zeros, and if you have it in this form, x minus a square and x minus b, in this form you can identify where it's increasing, where it's decreasing. But if it's in some complicated form, x to the power 5 and something, and then you have it in this way, and if this is your derivative, then if this turns out to be the derivative, let's say this is a polynomial, then if you will discuss, you'll need one interval, and let's say x naught is the point that you're, it's one of the critical points. And if you're checking at this point, you can't just check at one point, no, because you don't know where the zeros are of this polynomial, right? Does that make sense? You have to check at this point, so you have to make sure that your function is, if you want this point to be a local maxima, then you would want that your derivative should be positive here. So in this entire thing it should be positive, in this entire thing it should be negative, but you don't know if you have a zero here or not, because the polynomial, you don't know all the zeros of this polynomial, right?
Okay, ma'am. My point was that, ma'am, just 1 point before that, like it has to be increasing because it's a local minima. So like it has to be
How?
increasing just one
That's
point
what we're
before that.
looking for. We don't
Yeah.
know if, we don't know it's a local minima yet. We just know that f dash x naught is 0. That's all we know.
Mm.
We don't know if it's a local maxima or a local minima, or if it's neither.
What
So
if
if
there
it like
are multiple local minimas within a 1 point difference?
Yeah,
You understand? Within that 1 point, what if there are multiple minima, local minima, and multiple local maxima? It can be even very small, no? Wave can be any form.
The point is, if let's say you have this point and this is one of the roots of f. If you're saying this is going to be one, this is one of the roots of f dash, right? But there could be other roots too. So if you have this thing, you're saying you'll put this here, you have this positive. Here you have it positive, f dash, and here you have it negative. But in somewhere in between this thing, there could be other zeros, right? So if this is also a zero,
Yeah, you
at
need
this point
adjacent
your function,
roots.
yeah.
If they're not adjacent, then you won't be able to.
If this was the point you checked that, you said the derivative was positive here. Now if you have a zero here of the derivative, I'm talking about the derivative, then you might have the things negative here, right? So till here your derivative was positive, now it's negative, and maybe here it's also negative. Then how do you know that the sign is changing or not? Does that make sense now?
Yeah, ma'am.
Okay. So these are two things, and if your f dash x naught turns out to be zero, then it's a ring conclusive. Then you can say that your this double derivative test fails here. Inconclusive means you can't conclude from here if it's a local maxima, local minima, or a saddle. So that's the double derivative test, which obviously is easier unless you get your f double dash x naught equals to zero. That's the only problem here. Otherwise, it's obviously easier to test.
Can we say that if f double dash x is equal to 0, it's a saddle point?
No, no, it's inconclusive only. Inconclusive means you can't decide. You'll need you will have to use other things to find out what point it is. You can't conclude from here. Okay, and then let's just do one example on this local maxima minima thing. So let's say you have x by n and n by x. When I said that there could be other ways to figure out if it has a local maxima, local minima, or what that given point is. Let's say you have fx. You can do this question without using the double derivative test. Double derivative test is obviously going to be easier, but this can be done without double derivative test. So let's say you have fx equal to this function. Then firstly, we'll try to figure out the critical points, right? To figure out if it has a local maxima, minima, or what is it. So firstly, we'll do f dash x. So it will be 1 by n minus nx squared. This thing equals 0. And this will be x squared minus n squared by x square n. So you will just substitute this thing equals to 0, right? So this will be x equals to plus minus n. So the roots of f dash x here are plus minus n. And let's say you're taking n to be, let's not go there. Let's take n to be greater than 0. If this condition, this is one of the questions from your practice assignment or somewhere only. Uh, so if your n is given to be greater than 0, then and you have to figure out if your n is local maxima, or let's just forget this thing too. If you have to figure out if it's a local maxima or a local minima, then the first thing that you do is, first obvious way is to do this thing. F dash double x equals to 0, you'll substitute, no, 0. This you'll check, right? So you'll check f double dash n, you'll check, right? So a double derivative is minus and then 2 times n and x cube, right? This will be plus. This is going to be the double derivative. F double dash x. And if I substitute x equals to n cube, x equals to n, then I'll have 2n by n cube, which is 2 by n squared, which is greater than 0, right? So that means your n is local minima. That's one way to figure out that it's a local minima. So x equals to n is a local minima for this function. And the other way could be, let's say you don't want to use the double derivative test. The first thing that you do is you try putting things here. So it will be n, and if I'll put x equals to n, I'm going to get n by n plus n by n. So this is your fn, which is going to be 2. And then if I'll put anything else here, or let's just, I'm doing things, if you'll put x greater than n, let's say. For this one, you'll have, this thing is going to be x square plus n square. I'm rewriting this thing x square plus n square and nx. And now you're taking x greater than n. That means you can rewrite this thing as n square. Let's take the other case. Let's first take x less than n. So you can have n square and n square here. And here you will have n square. Let's replace this n by x. So this will be x square. You can replace this x by n here because your n is greater. We are using this greater symbol. That's why we're replacing x with something greater here. And for this, and here we're replacing the n by x. So in simple words, because your x is less than n, that's why your 1 by x should be greater than 1 by n. So if this is your 1 by n, this thing, this is 1
Ma'am,
by
in the
n for this
denominator,
function, right?
why, ma'am, in the denominator, why you replace n by x? It should be like we should replace x by n, na?
That's why I'm telling here. If your x is less than n, that means your 1 by x is greater than 1 by n, right? And if I want to make this function bigger, then I should be replacing the elements here to make, how would I make, obviously for the numerator, I can just replace x by n because n is greater than x, right? But if I do the same thing here, I should be, it's like this thing. You have 1 by x here and then 1 by n here. So to make this thing bigger, I should be replacing 1 by n with 1 by x, right? So this thing will be x square plus n square, which was your original fx, less than 2n square by x square, right? And you have taken x less than n. That means your x square is less than n square. And your n square by x square is greater than 1. That means 2 times this thing is this. So you can just replace this thing by this thing. You're not getting an upper bound here. The case we've taken is x n less than x less than n. Maybe then we should try something else. Then we should manipulate on the other side then. You should just replace this thing by 2x square and here you'll have n square. That's going to cause the same problem. Hmm. x by n less than 1, x square by n square less than 1. So this thing will be greater than this, right? We're having the same trouble here.
Ma'am,
Yes.
this was the function you were telling about x upon n plus n upon x. We are working on that
Yeah.
function, na?
Yeah, this function. This gives you n square plus x square by nx. And then this is greater than 2, which is what we have to prove. If I'll take x greater than n, then it will be fine. Because if you take x greater than n, here you'll have n square, here you'll have x square. This will be n by x less than 1. So 2n square by x square will be less than 2. So this entire thing is going to be less than 2. So for x greater than n, you'll have this thing less than 2. That means this thing less than 2. Okay, let's just skip this method for now. This is a method where you substitute things and find out on your own. It's not
Here,
a
what
very
you were doing
definitive
was,
method.
ma'am, just I want to say one thing. Here, this function was n upon x plus x upon n is equal to 2. So when like you
So
were
not equals
differentiating it
to
and
2.
making it less than 2 and more than 2 in order to find the local minima. That was your point, ma'am?
No,
Uh,
I was just trying to do that even if your n is less than x or your x is less than n, if we would have gotten fx greater than 2, then this point would have been a local minima, right?
f
So
dash
I
x, na
was trying
ma'am?
to
F
do that.
dash x. You are saying f dash x here, na?
No, fx only. We are trying to find the local minima, right?
Yeah. For that, we have to differentiate it, na ma'am?
Differentiate only. Okay, you differentiate things only to find there are 2 points here when you discuss a function. So for this point, for the x coordinate, you differentiate things. For the y coordinate, it's just this height, right? To differentiate f dash x and you put it equals to 0. Let's say you get the point x naught here. Then this point is x naught and f of x naught, right? So if you have to check if this is a point of local maxima or not, what you do is you test if this is the maximum value in a certain interval or not, right? In this interval, it should be the maximum value. That's your
The
idea.
last point, ma'am, can you repeat what did you said the last point?
In this one,
Yeah, ma'am.
you don't consider the derivative here because, okay, when I say if you have to prove that your 2 is the point of local maxima, by that I mean that your y is equals to 2 is the maximum height in some interval, right? In this interval, your y equals to this. This is the maximum height. So how do you do it? You do it for an interval, but I was trying to do it for the entire real line where I was trying to check that your fx is always greater than this 2. If your function is always greater than 2, that means your function, this is the minimum of your function, right?
So that would make it as global minima, right? Not local minima.
Yeah, that will be a global minima.
Okay. Okay.
So, ma'am, when we differentiate, like here, you are saying that the two is the minima. You were saying that, na? The two was
Yeah,
minima here. So yeah. So
not
just
2. N is
the
the minima here, right?
yeah, yeah.
It's n is the minima here. I don't know where 2 came into picture from. Yeah, from here it came. Okay, that's right. N is the x coordinate, and this is the y coordinate of the maximum point that you find here, this point. And let's just not go by this approach, but because it's not turning out to be correct, let's go by the double derivative approach for this question.
In the double derivative, we got plus or minus n, no? We checked only for plus n.
Yeah, for minus n also you can check. The double derivative is, what was the double derivative? This was the double derivative.
No, double
No,
derivative
not
was
this
squared
one.
by
This
x
one.
cube. That one.
Yeah. If you'll put minus f double derivative
Minus
of minus
10.
n, you'll have
You get minus
2n
2n by n cube. Yeah, minus
minus
n
n
cube.
cube.
Minus 2 by n square.
So this is
So
less than
minus
0,
n
right?
is a maximum.
Yeah, that's a point of local maxima, and the other one was a
Okay.
point of local minimum.
Okay, got it.
Here, when we put n less than like n less than a little less, then it would be positive also, na? It's a negative. Okay, okay, got it, ma'am. That point.
Okay. Then we have something called point of inflection. So where your point of inflection is what happens in a point of inflection is your function changes its concavity. Concavity means if your function is, this is called concave up. If your function is like this, then it's called concave up. And this thing is called concave down. So sometimes what happens is a function looks like this, right? So till this point here, it's changing its concavity. So it's like till, and I can't just point the exact point here. I can't pinpoint that point. But this one is concave up and this one is concave down, right? So somewhere near this point only, a function is changing its concavity from up to down. That point is called a point of inflection. Concavity changes of the function. How do we say this? So a function concavity up is given by this thing f double dash x greater than 0. So if in an interval you see that if f double dash x is greater than 0, in let's say x naught minus epsilon and x naught plus epsilon. Oh, this implies f is concave up in this interval, or let's just not even mention the interval, even if I just say I. Let's say we have an interval I and your f double dash x is greater than 0 in this interval I. That means for every point in I, your f double dash x is greater than 0. That means your f is concave up in I. And then if there is a point, so for point of inflection, what do you want? You want the concavity to change, right? So that means your x naught is a point of inflection if f double dash x is greater than 0 for x naught minus epsilon and x naught. Why are we taking x naught minus epsilon and x naught? This is the interval before x naught, right? Yeah, x naught minus epsilon. So to indicate the interval that is on the left of x naught, we write x naught minus epsilon and x naught. So if this is greater than 0 for all x belonging to this interval, and f double dash x is less than 0 for all x, this is the symbol for all x belonging to x naught and x naught plus epsilon. Or you can take the opposite too. So here I'm mentioning greater than 0 or less than 0. So in the bracket, if you're replacing with this bracket, if you're keeping greater here, then make sure you're keeping less here. If you're keeping less than here, then make sure that you're taking this one. So with this bracket one, take the bracket one. With the non-bracket one, take the non-bracket one. That's your definition for point of inflection. Is this part clear to everyone?
Ma'am, that x naught minus epsilon, comma x naught, what is the significance of that? Like graphically speaking?
It's just the
And x naught?
interval. It's this thing. We know that if there is an interval, we
Okay,
just
okay.
discuss this thing. Let's say this is the point x naught. If there is an interval, let's say this is the interval I. where f double dash x naught or your f double dash x in every point from here, if your f double dash x is greater than 0 for every point here in this interval, then it's concave up, right? It's concave up. So your f double dash x should be greater than 0 here on this side. And on this side, f double dash x should be less than 0, right? So for this interval only, you write x naught minus epsilon so that you get an interval on the left. If you will take x naught minus epsilon to x naught, that means it's an interval on the left of x naught, right? And if you will take x naught to x naught plus epsilon, that means it's an interval on the right of x naught, including x naught, right? That's why we're taking this thing.
How is it different from the point of local maxima and local minima, this point of inflection?
Okay, in your point local maxima and minima, your derivative sign change, if you have noted that thing. So that means after that point, your derivative represents, this is an important thing for you to remember the difference between these two. So when we talk about the derivative, we mean increasing, decreasing, right? So if you have this greater than 0, that means your function is increasing. If you have this less than 0, that means if your f dash x is less than 0, that means at point x, your function is increasing. Sorry, greater than 0. And if your f dash x is less than 0, that means your function at this point x is decreasing, right? So when we say that your f dash changes sign, that means from increasing, it goes to decreasing after a point. So before this point, it was increasing, then it goes to decreasing. Then we say that it's a point of local maxima, right? And if the opposite happens, then it's the point of local minima. But when we're discussing the concavity, concavity is given by the double derivative. So if this thing is greater than 0, that means it's concave up function. If this
But
thing is less than 0,
not using double derivative test in local maxima and local minima also, then it's getting confusing.
yeah, you're using that. But
Ma'am, one thing, what
in
you
that
said
one,
at
you
point,
just,
ma'am,
yeah,
ma'am, in point of inflection, when you said f double dash x is more than 0, okay, so that is conclave up, you are saying that in
yeah,
a way. Yeah, ma'am. And when f double dash x is less than 0, you are saying it is conclave down.
yeah.
So in this, do we also define a point, local minima point or local maxima?
Local
Can we
minima will be
define
here
that?
only, no? That's why you have
Okay,
if you
okay,
have f
okay,
double
okay.
dash x, for this one you will have f double dash x greater than 0. So if you have
Mhm.
something like this, then you will have a point here, which will be a point of local minima. But we already know
Just
that
before
at
that,
this point, not just before that, if this and what just before what?
just
If this
before
is
the
a
rate
point,
become positive, na? Because okay, okay.
let me complete first. If you have someone had a doubt and they had a confusion in, they're using this double derivative in both the point of inflection, that means in the concavity concept and in the maxima minima concept. But in concavity, when you have concave up thing, you have a point of local minima, right? When you have concave down, you have a point of local maxima. In fact, it should be easier for you to remember this thing because for concave up, the double derivative should be greater than 0. And when you have concave up, then only you can have a point of minima here, right? That's when your double derivative at x naught is also going to be greater than 0.
Yes,
Is
ma'am. Now
this
it's clear.
is this defining it as inflection point is the same as defining it as turning point?
Yeah, it's the same as a turning point. Yeah, point of inflection is the same as your. No, point of inflection is not your turning point. Point of inflection is where your.
Point of inflection is also saddle point.
Point of inflection is not. No, its saddle point is actually different. And
Point of inflection
first
is, ma'am,
point
just
is point of
after.
inflection. Just hold on a second. Point of inflection and what was the other thing that someone was asking?
Turning point.
Turning point.
Turning point. They're totally different than each other. Its turning point is where your graph turns. So it's like this thing. So this is called a turning point now. But if you have something like this like in x cube, so in x cube, what happens is this goes. Now this is actually not a turning point. Why? Because you're not turning things. So in literal definition sense, it's not a turning point, and then your derivative just keeps increasing. So here your derivative is positive, and then after this point, your derivative is also positive, right?
So in the video lectures, what was explained by Professor Sarang was that when he had explained this point, he had called it as turning point only, that from upward to downward the concavity is changing, but he said that it is a saddle point.
It is mentioned that saddle point and inflection points are same, even in the book provided.
Yeah,
So
saddle point and
So, but
it's
inflection point.
confusing
actually, a
right now.
saddle point and point of inflections have difference between them. In your book, that it might have been given the same, but they're not the same. But if it's given in your book, that means you have to consider them same only. And
The
this is
point
not
you
in
told
your
about,
course, but point of inflection is actually where your concavity changes. And saddle point is where it's neither a point of local maxima nor a point of local minima. So your saddle point is actually always a critical point. Saddle point is always a critical point, but your point of inflection might not be a critical point.
So can you help us understand this through drawing all 3 points on a graph, because that would be much better for us to
Yeah,
understand.
it's that
can you just
sometimes we
explain the
just
point of
consider.
inflection once? The point of inflection that you just explained, can you just explain that once? Point of inflection through that graph, yeah, on the cursor.
Let me just clarify the difference between a point of inflection and a saddle point. But if it's given in your lectures, then you're supposed to take them same only, because your exams and everything will be based on your lectures and your books only. So point of inflection, saddle point, you can consider the same, but point of inflection is actually where point of inflection is about concavity, where concavity changes. Whereas your saddle point is a point which is not a point of local maxima and not a point of local minima, and they're not always same. Like in this one, when you have this thing x cube plus x, now if you take the derivative of this, it will be 3x square plus 1, right? And 0 is not a critical point of this function, right? 0 is not a critical point of this function, but it's a saddle point, because not a saddle point, it's a point of inflection. Because what point of inflection does is, if you look at the graph of this function, then you will see that it's not changing its direction. Or you can do the double derivative thing here. Now, if you take the double derivative, you don't even have to go till the graph thing. You don't even have to analyze the graph. The double derivative is 6x, right? So now to decide if your concavity changes or not, your 6x changes sign at 0, right? And we know that when your f double dash x is greater than 0, for x greater than 0, it's 6x only, right? And your f double dash x is less than 0, for x less than 0. That means your concavity is changing, right? This is concave up. Before 0, it's concave up. After 0, it's concave down.
Can
So
you draw this
technically,
on a,
this is a point of inflection.
can you please draw this on a graph, because it's still getting very confusing.
You can try this on Desmos, because it's not one of the very the typical graphs that we draw here. So you can try this on Desmos and you will be able to see
Ma'am,
that
when you
x
said
equals to
it,
0.
f double s, ma'am,
Just
when you
wait
said
a
that f,
second. Hold on. Let me just complete this thing first. So this point, my point here is that your x equals to 0 in this case is a point of inflection, because it changes its concavity. At 0, before 0, it's concave down. After 0, it's concave up. That's why it's a point of inflection. But it's not a point of, it's not a saddle point, because your derivative is not 0 there. The saddle point is a critical point where your derivative is considered to be 0. But if your book says so that it treats your saddle point and point of inflection as same, then you're supposed to consider the saddle point and point of inflection same. Consider them to be same only. Is that okay?
Ma'am,
Yes.
so we can say like saddle point can be point of inflection, but point of inflection cannot be saddle point, correct?
As per your book, they're both same. So let's stick to that only. I was just
Okay.
trying to make a clear. I was just trying to tell you the difference because there is a difference between these two points.
Okay.
In general and in other books, there is a difference, but if your book says so, then let's just stick to this thing only. Point of inflection to be the same as saddle point. Yes. Now, if anyone has any other doubt, you can ask that.
Ma'am, I had one that you said f double dash x more than 0. You said that there
Yeah.
will be a point of, like at 0, there is a point of inflection. You said that,
Yeah.
na, ma'am? So at f double dash f double dash x more than 0, there is a concave up. You are saying that for all the values of x
Yeah.
more than 0, we will have a concave up. And all those values less than 0, we will have a concave down. That was your point, ma'am.
Yeah.
And at 0, you are saying that there is a point of inflection. Yeah, ma'am. So if we draw it graphically, like if suppose we draw it graphically, how does it look like?
I don't know how the point exactly looks, but if it says that, let's say this is your zero, I'm just drawing a very rough sketch. So after greater than zero, it's concave up, so it should be this way. And before zero, it's concave down, so it should be this way. So it's something like this.
Okay, ma'am. And obviously, when f double dash x would be 0, that would be 3x square plus 1 is equal to 0. So minus 1 by 3 under root,
Is the
that point
critical
would be a
point.
local
Yeah.
maxima and local minima there. Yeah, ma'am. So you also mentioned that just before f double dash x more than 0, it's a concave up. So there should be a local minima also, na, ma'am, there, because it is going concave up f double dash x more than 0, na?
There will be a local minima. No, if this goes like this thing, then there will
Mhm.
be something like this.
A kind of a local minima.
Yeah.
And what about the saddle point according to your perspective? That you said that this is, according to you, it's point of inflection. So what according to you
Saddle
was
point is a point.
saddle point?
Its definition is here. As per the proper definition of a saddle point, it's the point, it's a critical point. It comes under the category of critical points where derivative is zero. That means firstly, the first condition for it to be a saddle point is that f dash x should be zero, and then it should not be a point of local maxima and a point of local minimum. That's fine. So what
Basically,
happens here
saddle
is
point is
at
a
this point
point.
also, yeah,
So basically, saddle point is a point where the tangent is zero, inflection tangent is not zero.
so
Both are not local maximum or local minimum.
yeah, it's just a critical point. That means a saddle point is a point where your derivative is zero, but it's not a
Correct.
point of
So
local maxima and not a point of local minima. Now the
yeah,
problem
so
here
it should
is
be
that your
flat.
zero, yeah,
Yeah. Okay. At zero, it
plane
So
should
ma'am,
should
at
be
when
in
that
we
flat
cut.
only.
No inflection, it cannot. It need not be flat, but saddle point, it should be flat.
Yeah,
Correct.
correct.
so ma'am, when we go to that function x cube plus x, just the function that you wrote x cube plus x, when we double differentiate it, it would be
Yeah,
6x. Like 6x would be 0. So at x is equal to 0, you are saying that there will be a saddle point. Yeah, ma'am.
there's a point of inflection. And I
Yeah,
don't want
point
to
of
get into
inflection.
the
Okay, okay, okay.
details of this. I've
Okay,
already
okay,
said
okay, ma'am.
just consider these two things to be equal because that's what your textbook says. So stick to this only.
One small thing here, just I'll close it out here. So in x cube plus x equal to zero is inflection point.
Yeah, it's
X
an
cube plus
inflection point.
x is equal to zero is an inflection point. But in
Yeah,
x cube, x is equal to zero is the saddle point. Correct?
it's a
X
saddle
cube.
point and it's a point of inflection both there. So in x cube, your x equals to zero is a saddle point because obviously your derivative is also zero at
Correct.
this point.
Zero. But you're
So
saying that's
it's a
also inflection.
yeah, it's a
Okay.
point of
Oh yeah, yeah.
inflection too.
Okay, okay, got
It's
it.
both here.
Thank you.
Ma'am, the only condition for a saddle point is that double differentiate has to be 0, na? That is the thing. Yeah, am I correct?
The only condition for your saddle point is that the derivative should be 0 here, and it should not be a point of maxima and minima. When you can guarantee that it's not a point of maxima and minima, then you say that it's a saddle point. You don't decide by f double dash equals 0.
And if f double dash x is 0, then we cannot say it, like it's inconclusive.
Yeah,
You said
it's
before.
inconclusive.
Okay.
Okay. Then moving on, we'll come to Riemann sums now. So Riemann sums is, and before moving to Riemann sums, let's just discuss partitions of an interval first. I hope everyone knows what an interval is. So partition is, let's say you have an interval this, A, B. Then the partition of this interval we consider as x naught equals, we start from this point, and then we take x1, x2, x3. Now these points do not have to be equidistant. We don't mean that we're dividing this partition into equal parts. This could be 1 unit, this could be 10 units, this could be 0.5 units. So we're randomly dividing this thing. And B, we are taking as x5. So in this case, your x0, x1, x2, and x5, this thing will be a partition. This is called a partition of this interval AB. So in simple words, you divide AB into parts where your first part, this one is A, the last one is B, and these numbers have to be finite. So the number of x naughts or your xi's, the number of xi's should be finite. Then you say that your partition, this is called a partition. Is that fine? So when you divide an interval into some parts, into some finite parts, then these points, x0, x1, x2, when collected together, give you a partition. This is your partition. Then this thing, there is this thing which is called the norm of partition. So your norm of partition means the length of this. So before coming to the norm of partition, we'll discuss delta xi. So delta xi is basically your xi minus 1. What does this mean? That if you have this thing, let's say you have x0, x1, x2, you've partitioned your interval into this, and x3 equals to b. Then your delta xi's would be the length of these intervals. So this interval, the length of this is x1 minus x0. Then the length of second one is x2 minus x1, and the length of third one is x3 minus x2. So these are called delta xi's, right? This is delta x1, this is delta x2, this is delta x3, right? If there were more of these, then we would do both. And then when you take the maximum, so this is called the norm of partition, which is also the maximum of, so this is how it's defined, delta xi's. So your norm will be the maximum of these values, right? So for an example, let's say you have this 1 to 10, and you have divided it into 2, then 3, then 7, then 9, and then 10. Then what's the partition of this? This is an interval from 1 to 10. What's the partition here?
3, 7, 9.
1 is also included, right? We include x0. 1, 2, 3, 7, 9, and 10. This is the partition. And then what's the norm of P? Let's come to delta xi's first. So your delta x1 is 1. Then delta x2 is 1. Again, then delta x3 is 4. Delta x4 is 2. And then delta x5 is 1 again, right? And what's the maximum of these? So the maximum of your delta xi's, which is also called the partition of the norm of this partition, is 4, right? The maximum of these quantities, it's 4. So the norm for this partition is 4. Is norm and partition and everything that we've discussed so far clear? Then we can come to Riemann sums if this part is
Yeah,
clear.
ma'am, understood.
Okay. So let's say if you have been given this function, and you have to find the Riemann sum from this point A to this point B. And we know firstly we need, for Riemann sum, first thing we need is the partition. So partition is, it starts from here x naught and ends at xn, where xn is n is obviously a finite number. N could be 5, 10, 15, anything, but it's a finite number, right? This is it. And then you've divided it further x1, and here you have xn. And then next up, you take points in these intervals. So for a Riemann sum, and those points also you're mentioned. So in this interval, let's say I'm taking x1 star point, x1 star. In the next interval, let's say I'm taking x2 star point. Any random point we're taking in these intervals. In the next one, let's say I'm taking x3 star, and so on, so on. I take till xn. So I'll be left with xn, these points, right? So from each interval, I've taken these points. These points are generally given to you in questions. Not generally, they're always given. So whenever you're asked to find the Riemann sum, you're given these points. So how do you find the Riemann sum? Riemann sum does this to your function. So instead of finding the area under this curve, what we do is we try to divide it into first intervals. So these are intervals, and then we take the height equal to the height of this point. So at, let's say at x1 star, your height is this, right? At x1 star point, your height is this, and then we take height of all equal to this. So for this entire interval, we take the height to be this. In this interval, can you guys see that the function's height is actually changing, right? From a to x1, your function is this. So its height is actually changing, but we've taken a constant height. And what height have we taken? We have taken the height at x1 star. This is the height fx1 star, right? We have taken this height, and we've considered the height for all these to be same. Same is the case with all the other intervals. And then we find the area under these. So let's say here you have here. So for this entire interval, you take the function's height or the height to be the height at fx2 star. This height is fx2 star. This height was fx1 star. And then you take the sum of all of these. Right, so what you're doing is this length you take, which is your x1 minus x0, and then you multiply it with fx1 star. What does it give you then? What does this thing give you? This
The
height
area of the
is
rectangle.
fx1
Area of the
star.
rectangle.
This height is fx1 star, and this width is x1 minus x4. So it's going to give you the area of this thing, right? This one. Same you do with the other one. You take fx2 star, and then you multiply it with x2 minus x1. So it's going to give you the area, this area, right? It's not giving you the area under this curve. It's just giving you the area under this thing. And same you do with other points. So you do this thing till fxn star, xn minus 1, which you can write as fxi star, xi minus 1, I varying from 1 to n, right? So this is called your
Ma'am,
Riemann sum. Yes.
when you wrote that x1 minus x0 into f x1 star,
Yeah.
uh, this what you wrote. So can we say that x1 minus x0 is equal to x1 star? Is it x1 minus x0 is
What we do here
x1
is we
star?
take a function and we divide it into intervals. Let's just take two intervals for clarity. This is, let's say, x0, x1, and this is x2. So your partitions are x0, x1, x2, and your intervals are x0, x1. This is first interval, and then x1, x2, right? So what we're doing here is we're taking a random point. X1 star is not a particular point. It's a point that is given in the question. You'll be given this point in the question that you take from this interval. So you take a point from this interval, and that could be any point. It will be given to you in the question. Let's say this is that given point. And then you take the height of this. Now we know that in this interval, the function's height is changing, right? First it's this, then it's this, then it's this, then it's this. It keeps changing, right? This distance keeps changing in this interval, right? But if we fix it to the height of this one, now this one is, this entire thing is fx1 star, right? This height. Now if instead of taking this entire area is this, under this entire curve, but if I just take this rectangle, now what's the area of this one? It's x1 minus x0 here. And then you take this height, right? So it's fx, this height is fx1 star. So fx1 star for the height, and this for the length, this one on x-axis. x1 minus x0 gives you this length, right? Same case you do here. You take up a random point x2 star here, and then you take the height here. So let's say its height is here. So this is fx2 star. And then you take this entire area. You take this area under this line, right? Where this line is a straight line whose height is fx1 star, fx2 star. Is that okay?
Yes, no.
Okay. This is called the Riemann sum. And what is given to you to calculate Riemann sums? So first thing given to you is obviously the interval, then the partitions. The partition is given to you, and then the point also. The xi stars that you have to take, those are also given to you, right? You need these three things to find, and obviously the function is given to you. So to find this Riemann sum of a function, you need the function, then obviously the interval, then the partitions of that interval, and then xi stars for each interval. That is what you're going to need to find the Riemann sum. And then there is left Riemann sum and right Riemann sum. So in left Riemann sum, what you're doing here is to divide it into partitions x0, x1, and x1 star that you take is some point in this interval, right? x2 star is something that you take, some point that you take in the next interval here. So if you take x1 star equals to x0, x2 star equals to x1. That means if you shift all these to the left once, then it's called the left Riemann sum or left hand Riemann sum. And if you shift these to the right side, that is, if you take x1 star equals to x1, x2 star equals to x2, then that's your right hand Riemann sum. So, looking for a question on this one. Here. This is one question from your graded your activity questions, in which the function is given to be 3x plus 1. So the function is given to you. Then
Ma'am,
the partition is also given. Yes.
Ma'am, there was also a question about middle hand, like middle sum. What is
Yeah,
middle?
middle Riemann sum is just Thanks for reminding me. This middle Riemann sum is when you take your x1 star to be the center of x0 and x1. So if you take x1 star to be in the center, that's your middle Riemann sum.
Okay. So do we take like average of those two or just the center? Oh, we do average, right?
Yeah, the average would be the center. No?
Okay, yeah, I got it. Thank you.
The intervals, then the intervals given to you, and then the
There
partitions
were
are also
two more. There were two more Riemann sums. What?
which one?
There were two more actually.
Two more Riemann sums.
Yeah,
Yeah, he
left,
had
right,
also
middle.
mentioned about upper Riemann sum and lower Riemann sum.
Upper Riemann sum. No point.
Okay. So your upper for your upper Riemann sum, you take the maximum of that function. So here in this one, what we were doing is we were taking a point from x0, x1, so x2, and so on, so on. Let's say you have this. This is A, and you have B here. B equals xn. Then if this is your function, what we were doing was we were taking a random pointer. Now instead of this, if you take the maximum height, so this is your maximum height, right? This is your maximum height. And if you take this thing, if you fix your height to be this maximum height, and also in this interval too, you fix what's the maximum here. I think it's this point. So if you fix here, you will fix this height. And that gives
Oh,
you your
that's how
upper
it's
Riemann
giving
sum.
the upper bound. Okay, okay.
Yeah,
So that's how
the
this is the
up,
upper bound of. Okay.
yes, that
So lower
because each time
Riemann
you'll
sum.
get a bigger height, no? If
Yeah.
in simple words, if your function is like this, and if these are your partitions, then each time you take the maximum. So in this, you take the maximum height to be this. So you'll find, instead of finding the area under just this curve, you'll find the area this, right? So in this too, the maximum height is this. In this entire interval, the maximum height is this. So you should be taking this as height. So your area would be this. Here too, you'll get the area larger than under this curve. So that means your upper Riemann sum is always going to be greater than the actual area. And your lower Riemann sum is just the opposite. So it's always going to be less than the area.
Ma'am, what you displayed in the graph that you made, that is an upper Riemann sum, na?
Yeah, this one's an upper Riemann sum. And the lower
Okay.
one would be this. Should I draw the lower one too? So if you take the exact function and the exact partitions, then here the lower Riemann should be this one.
Here left and right are also same, no? Up and low.
What?
In this example. Okay.
Here you will take this and then here this. So the area that you will actually be considering under the lower Riemann sum is this, which is lesser than the actual area. Your actual area is this entire one, but you're only considering this one, right?
Ma'am, so how do we like implement while solving a problem, like for upper and lower? Like, do we just take the
Generally, you would be given, yeah, if you're not be given functions where what happens is if you've been given a random function, then and if you also are given the partitions always, right? In the so you will first have to take this partition and then you'll have to see where your maximum lies. Then that maximum height you'll have to consider and multiply it with this length.
Okay, so for each interval we have to find maximum height,
You
right?
won't be given questions like that.
Okay, just
Because
ask.
if it's a complicated function, each time you can't be finding all the local maximas and then do this thing, right?
Okay, got it. Thank you.
Ma'am, just one thing, when you were explaining upper Riemann sum, from where we got this definition and from where we concluded that it's a upper Riemann uh, sum, from where it came? From
From
which
where as
points?
in,
From which
no, no,
points this
these
this
points
became?
Are you talking about the xi stars?
Yeah. How did we
So you
got
don't
that?
take xi stars there. We instead focus on fxi stars. So that means your formula is this, right? Xi minus xi minus 1, and then you multiply it with fxi star, where xi star is a given point. Now, if they say that you have to find the upper Riemann sum, that means you have to find the maximum of that function in this interval. That means in x0 to x1, you have to find the maximum of the function. That is your fxi star.
And for the lower
For
Riemann
the
sum,
lower
the
one,
formula
you
is.
need the local minima or the minima in this interval. So in this interval, x0 and x1, for upper Riemann sum, look for the maxima. For lower Riemann sum, look for the minima. And actually, the local would not work, so you'll have to consider the global one in this interval. Is that okay?
How local and global you are inculcating on that? Can you elaborate?
So local maxima means this point is called a local maxima, and this height, let's say this is the height. Let's say this is a function. Then this is a local maxima if you get an interval around this point where this is the maximum value, or where it first increases and then it decreases. That's called the local maxima, and this one will be a local minima. Now, in the case of global maxima and global minima, what happens is you consider it for the entire function. The global maxima is actually the maxima of the function. That means
I mean, that is fine,
you
but
don't
how you are implying those things in Riemann sum? I was saying that.
in Riemann sum. What you do is in upper Riemann sum. What did we do here? We're taking the maximum height in this interval, right? This is the maximum height, so we're taking it to be this height in this
So we are
interval. So
taking
in this
local.
interval,
So we are taking the local maxima in
you're
that
not
interval.
taking local. If this is an interval, local means you can take any interval. But now your interval is fixed here. That means if your function looks like this, you can't take this is also a local maxima in this one, but you can't take this one. You'll have to take this height. Does that
So
make
for the
sense?
upper Riemann sum, we are taking global maxima, na?
Yeah, global maxima in the interval only, not the entire
Okay.
global
Yeah.
maxima.
Yeah. And for the
Okay,
lower Riemann sum, we are taking global minima.
yeah, in the interval.
Yeah. Yeah.
Okay.
Okay. That was the thing.
So if this is a question and then your partitions are given to be 0, then 2 by n, then 4 by n, until 2. And we have to find the Riemann sum of this. So they're asking for the right Riemann sum, I guess. Or the left. Let's just do a simple right Riemann sum. So for right Riemann, for the right Riemann sum, first thing that you need is you do. So what points would you be taking? This is 0, 2 by n, 4 by n. And if you have to find the right Riemann sum, then what point should I be taking in this interval?
2 by n.
2 by n. And then for the next one, I should be taking 4 by n, and so on, right? Till 2. So for right Riemann, and then the function's value at this point. So it's f2 by n and the length of the interval. So the length of the interval is equal everywhere. Here it's 2 by n, right? Length of this interval is 2 by n. The length of this one's also 2 by n. The next one's also 2 by n. We've equally divided these things. This is 6 by n. This is also 2 by n. So length each time is 2 by n. So you multiply by 2 by n and then this f2 by n. Then again 2 by n, f4 by n. And so on till 2 by n, f2. Is this fine? Then you take 2 by n common, and find the values of your functions at the given points. So function is 3x plus 1. So you'll have 3, 2 by n plus 1 plus 3, 4 by n plus 1. How many times do we have the 1 here? It's n times, right? We have n number of points here. So it's n number of times. So you'll have 3, 2 by n plus 3, 4 by n till 3, 2n by n plus n. We've added all the ones here. And then 2 by n. So this will give you, if you multiply 2 by n with this n, you will get 2 here. And this thing is going to give you, let's take 3 common from everywhere because it's everywhere, right? And then also take 2 common from here, here and here. So you will get 2 here, you will be left, and let's take n2 from the numerator. So you'll have this thing. So you will be left with 1 plus 2 plus 3 till n. This expression is the same as this one. We've
Ma'am,
just
in
taken
the
things. Yeah.
ma'am, in the third last step, when you took common, how you took the common? Just
Take everything
before that.
common that you can. First, what we're doing is first we're taking this 2 out here.
No,
We're solving
no,
this.
ma'am. When you took the
Just
common
take
first time, plus one. When the plus one came, how did that came?
plus 1.
Just above it, just
This
above a
one.
little bit. Yeah, yeah, ma'am. How did this step
So
came?
you're just adding all the ones here. These
No, no,
ones are
just
n
before
number of
that.
times.
Just before that, ma'am. When you took common, just before that, a little up when you go.
This
Yeah,
one,
in this, ma'am. Yeah, ma'am.
2 by n is everywhere, no? In every term.
Yeah.
So you can take 2 by n common.
Okay. When we took it, then
2 by n common, and then it's just the function's value. The function is fx equals 3x plus 1.
okay.
So it gives you this. And then we just simplify it. What did we get here? 2 by n. We took 3 common and 2 common too. So we took 6 common and then common. So we were left with 1, 2, 3 till n. This will give you 12 by n square. And the sum is, sum of first n natural number is n plus 1 by 2.
Well,
Yes.
there is n also, right, at the end when we added
Yeah.
all.
There is n.
No, plus n.
There,
Ma'am, you
yeah.
cut the n no, with the
Yeah.
2n, so it became 2.
Yeah, we multiplied it with this thing.
Okay.
So here you will get 12. This will be 6. N plus 1 by n. So it's going to give you 1 plus 1 by n, 6 and 2. And if you'll take, this is going to be the sum, but if you're asked the area or something using the Riemann sums, it's you take n tending to infinity. So this is 6 plus 2, 8. Sometimes you're asked to find areas using the Riemann sums. So what we do here is, when we increase the number of partitions, now if these are these many partitions, there are, let's say, n number of partitions. If you increase the number of partitions, then your area becomes accurate. Like in this one, you might have an inaccurate area, this one or this one. But as you increase the number of partitions, the more number of partitions, the more accurate the area is. That means the more closer the area is to the actual area of this curve. So if you'll take n tending to infinity, because if you increase n, your area improves. So if you'll take n tending to infinity, you'll actually find the area under the curve. I'll just repeat this thing. When you have a function and you have partitions, let's say you have to find the area from here to here. This area you have to find. So you find the Riemann sums from here to here in this one. If you have three partitions and you're taking any random points, this, then you're going to get some area, right? Now that area would be close to the area of this, the area under this curve, but it won't be the exact area. But as you increase the number of partitions, so from 3 partitions, if you take 10 partitions, that area would be a better approximate of the actual area under this. And if you increase n, it would be even a better approximate of actual area. So as you increase n, you keep getting the area as closer to the actual area of the curve. So if you take n tending to infinity, that should be your area under the curve. So that's why
Ma'am,
we are
what we
doing n
solved,
tending to infinity.
ma'am, what we
This
solved in the
Riemann
Riemann
sum
sum
is,
was,
yeah,
yeah, ma'am, what we solved the Riemann sum was, it was through the right Riemann sum we solved.
yeah, to the right one.
Okay, and through left also when we do it in a way when we do n is equal to
Left also you'll get same.
infinity. Okay, okay, but this was through right Riemann sum we
Yeah,
did
this
that.
was through right one, and do you want me to do through the left one too?
Maybe just the beginning, ma'am.
Yeah. Okay.
A little bit beginning, not the full.
So in the left one, what we did was the partition was this 0, 2 by n, and then 4 by n. So in the left one, only the points change. Partition is obviously the same. This is 2n by n. In the right one, we were taking these points, right? 2 by n, then 4 by n, then 6 by n, then so on, then 2 by n. That means the end point of each partition, each interval. Now in this one, we take the left one, so you should be taking 0, then 2 by n, then 4 by n, and so on, so on. So you should be taking f0, f2 by n. So the length is again 2 by n only, right? So it will be this thing, plus 2 by n, f 2n by n, right? Which is 2 only. So you can keep 2 here. Here you should be taking 2n minus 1 by 2. Why? Because each time you take the left one, right? So if this is 0, 2 by n, then you have 4 by n, then 6 by n, and then so on till 2n by n. So just before this, you have 2n minus 1 by n, right? So in this one, you should be taking 0. Then in this one, you should be taking 2 by n. Then in this one, you should be taking 4 by n. This will be 2 by n, f of 4 by n, right? And in the end one, you should be taking the left end point. So if you should be taking 2n minus 1 by n. Is this okay?
How
So
did
this
you
will be
got
your,
the exact 2n minus 1 upon n? Can you a little bit throw some light? Like,
in the question, the formula is given to you. It's given as 2 cross I by n, where I varies from 1 to n. So it will be, you'll start from here, you'll get 2 by n. Then you'll put 2 here, you'll get 4 by n. Then at 3, you'll get 6 by n. At n minus 1, you'll get 2n minus 1 by n. And at n, you'll get 2n by n, which is 2 only.
I is the preceding one, you're saying. Just the preceding one.
Yeah, this
I
one,
here is
I is a number between 1 and n. That's
okay,
how
okay.
your partition in the
Okay,
question is given.
okay, ma'am.
Keeps varying. This one is for the left Riemann sum. Is this okay? Can we move to the integrals if this one's done?
Yes, ma'am.
Okay. So, integrals are, let's say you've been given a function fx, then your capital F is called an integral of if the derivative of this function is the same as this. That's why it's also called antiderivative. So your fx is integral of this small fx if you'll derivate this capital F and you will get small x. For example, let's say you have sine x. Then we know that the sine, so for the integral of sine x, I need a function which I'll when derivate, I'll get sine x. So I need a function. If I'll take the derivative of that function, I should be getting sine x. I need such a function. That function should be cos x, right? But cos x's derivative is minus sine x, so you should be taking minus cos x, right? Minus cos x is that function which when you will derivate, you will get sine x. Derivative of cos x is minus sine x, and derivative of minus cos x should be minus of minus sine x, so it's sine x, right? These are called integrals. And then let's say you have been given this thing fx from a to b, and you know that the integral of this thing is fx, or you have been given that f dash x equals to fx. So if this is given to you and this has been asked, that means this should be equal to f dash. This should be fb minus fa, right? Or in simple words, you can write it as f of x from a to b. Then you write it as fb minus fa. So you first write the integral of this thing, and then you put the limits in this manner. And then there are some important integrals that you should be keeping in mind. Let's do those. So the integral of x to the power n, this is the function and this is the function's integral. So for x to the power n, you have xn plus 1 by n plus 1. For e to the power x, you have e to the power x only. For a to the power x, it's a to the power x by natural log of a. When we used to take the derivative of a to the power x, it used to be a to the power x into natural log of a. So while taking the derivative, you multiply things. While taking the integral, you divide things. It's ax by natural log of a. It's because it's the reverse process of derivatives. That's why you do the opposite here. Then for integral of tan x, we have natural log of mod of secant x. Integral of secant x, we always write a dx here. It's natural log of secant x plus tan x. For cot x, we have natural log of sin x. And for cosecant, we have natural log of cosecant x minus cot x. And as we discussed that your integrals or integration is the reverse process of derivatives or differentiation. So first we'll be discussing some important derivatives too, so that you can easily see that if, for example, let's say you have cot inverse x, then its derivative is, these are derivatives. The previous ones were integrals. Then its derivative is minus 1. Let's start with cos first, maybe sine. For sine inverse x, we have 1 by square root of 1 minus x square. So 1 by square root of 1 minus x square is the derivative of sine inverse of x. That means if you integrate 1 by 1 plus square root of 1 minus x square, if you integrate this thing, you'll get sine x. That's a constant, obviously.
Will it be sin x or will it be sine inverse of x?
Yeah, sine inverse. So since it's the reverse process of this, it goes the opposite way. So if this is the derivative of this thing, that means this is the integral of this thing. And for cos inverse x, that's why we're discussing the derivatives of this. So cos inverse of x, you have 1 by square root of 1 minus x square with a negative sign. For tan inverse x, it's this thing. For cot inverse x, it's the negative of this only. For secant inverse x, we have 1 by x square root of x square minus 1. And for cosecant, it's the negative of this one, minus 1 by x square minus 1.
Do
Then
we
we
have
have some
to
other,
remember these?
what?
Do we have to remember these or will they be provided in the exam?
I think it's better if you remember these things because you don't have to remember all of these. It's easier if you remember these things because there are questions on integrals. I don't think they'll be in the exam. You won't be given these things in the exam. Then there are other integrals. The first one is this only. So the integral of this thing should be sine inverse of x. And then if we slightly change this thing, we get dx by square root of, instead of a1, we are taking a square this time. This integral becomes sine inverse of x by a plus constant. Then we have x square minus a square, which is natural log of mod x plus square root of x square minus a square. Just focus on the Riemann one more because this, even if you forget some of these, that's fine. If you remember all of these, that means you can actually solve all the questions from integrals, almost all. There'll be no question that you won't be able to do if you remember these things. Should I write down all these formulas or is it okay? Because there are some few more.
Ma'am, so we have to remember all of it, like.
One sec. These two are literally the same. How many are there? 1, 2, 3. There are just 3, 4 from here and then 3, 4 from here. And I think you have questions on this too. You have questions in your activity questions. The you've been given the integration of tan x and something else with it.
Ma'am, for the last one, that will be 1 by a tan inverse, right?
That's 1 by. Thanks.
And also it will be x by a.
check these formulas, there are some few more like these only where you can find these on internet. And there won't be a lot of questions from these, so you don't have to worry about this. Then we have, now this one's an important rule. It's called the Eilert rule. So when you have two functions, fx, or let's say u and v. So when you have two functions, ux and vx, and you have to integrate these two functions, then how do we integrate this thing? First, we take the ux function constant and integrate the vx function. Then we take this is in integral. Then we take the derivative of the ux function. This is not product, this is in integral. That means, okay, let's do a question on this. Let's do x sin x. So as per the formula, let's consider this to be u, this to be v. We'll come to the Eilert rule later. And how do we use that rule? But let's just first take this x to be u and sin x to be v. Then as per this rule, you should have x here, then integration of sin x, which is minus cos x. Then the derivative of u function, which is dx by dx. Then the integration of v function, which is minus cos x, right? And then the integration of this entire thing, This you'll get as minus x cos x minus integration of 1. This will be minus cos x and dx. This will be minus x cos x. And this minus and minus become plus. So this will be integration of cos x dx, which gives you sin x minus x cos x. So this is the required integral then. And how do you choose u and v? Because obviously, if you will take this to be u, this to be v, it will be different. And then if you take this to be u, this to be v, the process at least would be different. It might be possible that flipping these two would, in both ways, would give you the answer. But sometimes what happens is if you change these two things, then it becomes more complicated. So you have to choose your function, u function and v function very carefully. So for your u function, how do you choose u? You use the Eilert rule, which says your I stands for inverse trigonometric functions. Inverse trigonometric as in sine inverse, cos inverse and all. Then your L stands for logarithmic functions. A stands for arithmetic functions. Those are all your polynomials and everything, those functions. Then T stands for trigonometric functions. And E stands for exponential functions. A to the power x, e to the power x, all of these. So if you go in this order, and if you have a function fx, and if you have a function gx, and if your fx is from this category, say it's a logarithmic sort of function, and your gx is from this category, exponential function, then you should be choosing u as this one. You should choose fx as u. So u should be chosen in this order. If you have an inverse trigonometric function, choose that as u. If you have a log function, so if you have these two functions, you should be choosing the inverse trigonometric function as u. If you have these two functions, arithmetic function and exponential function, like this one, x squared e to the power x, one is an exponential function, the other one is an arithmetic function, then you should be choosing u as this. If you have log,
Why did you said
then you should be choosing u as this function, log function. So go in this order. Yeah, is there any doubt?
Ma'am, you said that we have to choose U and V very carefully because if we don't choose it, can it become a little complicated? Is it the reason?
Yeah, then you won't be able to solve it. As in, if you will choose in this one only, if you will take x square e to the power x, and if you will integrate it, now if you choose u to be this function, then you won't be able to solve this one. Because what happens is you will have e to the power x, then you will integrate x square. So integrating would increase the power x cube by 3 minus, then you take the derivative of this, which will be e to the power x.
It would just complicate it, but the answer would be the same, ma'am.
You won't be able to solve it this way. So what do we do here?
But
Integration of du by 1 second. Hold on a second and you will be able to see. So v function is x square. If you integrate it, you will get x cube by 3. So here you will get x cube by 3 dx. Now you will have to solve this integral. This one obviously you can solve, but then you will have to solve this integral ex x cube. Here you had x square. Now you have x cube. And if you use the same thing here, if you do the same thing here, you choose this as u, this as v, then you will end up with e to the power x and x to the power 4. In next step, you will end up with e to the power x to the power 4. You will keep going on like this. You won't be able to solve. This will never end if you keep choosing the wrong function. Is that okay?
okay, ma'am.
Clear.
So let's do one question on this then. X cube, let's do this one. Do I need to do this question now? Or can you guys try this one? It uses the same rule. Which function do you think should I be choosing as u in this?
ln logarithm.
Log.
Ma'am, logarithm ln x.
Yeah, choose this as u. You will have natural log of x, and then you have integration. And actually,
हाँ
please
दे दो
mute yourself. We'll do it this way. We'll have x to the power 4 by 4. And then we'll have the derivative of natural log. So derivative of natural log is 1 by x. And then integration of x cube, which is x to the power 4 by 4. Right? So it's x to the power 4 by 4. This will be natural log of x to the power 4 by 4 minus x cube. So this will be x to the power 4 by 16. I hope there's no calculation mistake here. This is u. This is integration of v. This is derivative of u. This thing is integration of v again. And then the entire integration. Is this okay? Or should I just solve it step by step?
Can you please do it step by step?
The function u is natural log of x. V function is x cube, right? So as per your formula, you should be doing ux. Keep ux as the same. And take the integral of vx, right? And then minus integral of derivative of ux. And then integral of v. So your ux is natural log of x. Then vx is x cube. Then the derivative of ux, right? The derivative of ux is 1 by x. derivative of natural log of x is 1 by x. Then you take the integral of this b, which is that integral of x cube, right? And then the integral of this entire thing. This integral is for this entire thing in brackets. This is natural log of x. This thing is x to the power 3 plus 1, so it's x to the power 4 by 4 minus. Then for this you have 1 by x and x cube, right? So you will get 1 by x, x to the power 4 by 4 dx. This term remains same, and here you will have integration of x cube by 4 dx, which gives you natural log of x into x to the power 4 by 4 minus x to the power 4 by 4, and you already have a 4 here, so it's this. Is this okay now?
No, this is integration by parts. Right?
Yeah,
So
it's
that's
integration by parts.
and what is integration substitution thing of the
What? Integration for integration by parts, this is the entire formula. This one. Is this understood?
Yes, ma'am, clear.
Okay. Then we have, let's say if you have minus a to a and you have a function fx dx. And this is given to be an odd function. Odd function means you have f minus x equals minus of fx. Let's say this is the property of this function. Then this integral should be 0. How does it turn out to be 0? You divide it into two. Let's say you have a to b fx. This is one of the properties of your integrals. So if you have integral from a to b, you can write it as, and let's say c is a point between a and b. So if you have 0 to 10 here, then you can write it as 0. And I know that 5 is between 0 to 10. So I can write this as from 0 to 5, and then fx from 5 to 10, right? So first I'm integrating this function. First I'm finding the area of this function from 0 to 5, then from 5 to 10, and then adding both of these. Or I can just directly find from 0 to 10. Same thing, right? So I can write this thing as minus a to 0 fx, and I'm assuming that your a is greater than 0. This thing, and then fx from 0 to a dx, right? There's one more property of, these are properties of
When we
integral.
just break it,
When you have,
when we just
yeah,
break it, so like from 0 to 10, so we took the point, the average point. Now we always have to take the average point. That is 5.
no, you can take any point. You can take 3 too. You can just write 0 to 3.
Okay, so this
Then,
property is
yeah,
only for the
it's
odd
like,
function.
it's, what does this integral represent? If you have this function, then this represents this entire thing. This thing represents the area of this function. If this is your fx, then the integral represents area from area under this function from 0 to 10, right? So it represents this thing. So either you find the area from 0 to 10 directly, or you find it from 0 to 1, then 1 to 2, then 2 to 3, then till 10. It's the same thing, right?
Okay, ma'am, and the property that you wrote, it's for the odd function only, the above
So
property.
this one is this one.
No, ma'am, the first one that you wrote,
That's the same
top left,
property. This is which one?
the top left one. Yeah, this one.
A
This is
to
for the
A,
odd function.
minus A to A.
Yeah, this one is for odd functions. This is when this is true. So when given this thing, then this thing is true. If this thing is given to, that means if a function is given to be odd, then this property is true. And then we have this property that if you have the area from A0 to A, you can just switch these things from A to 0. So if you take this thing, you'll have a minus here. Instead of taking from 0 to A, if you take from A to 0, you get a minus here. This is one of the properties of integrals, which we'll use here. Instead of taking from minus A to 0, you can
Ma'am,
just
can you
take
just
0 to A, 0 to minus A fx dx. And this is from 0 to A fx dx.
Can you put this through an example?
Wait,
Because that will just concrete the understanding much better.
Ma'am, one more thing. What you are erasing, from where it came?
it's just the proof of what I've written. Let's not do the proof here. Let's do
For
one
the odd
example
function.
on this property. It's again one of your activity questions. Let's take minus this area of this function x to the power 2021 cos 2021x plus sine 2021x. So if you have this thing, then we know x to the power 2n plus 1, 2n plus 1 for odd. So if you have x to the power some odd number, then if this is your fx, then f of minus x is the same as minus of fx, isn't it? You can take the minus out, right? If you have x cubed and I'll do minus x cubed, then I can just write it as minus of x cubed. For odd powers, you can take the negative sign out. And for even powers, it gets absorbed, right? So here, your x to the power 2021, because 2021 is, what's an odd function? Odd function is where your f of minus x is the same as fx, right? And when you have an odd function, then the integral of that function from minus a to a is 0. Now we have minus a to a. We just have to make sure that this entire function is an odd function, right? So let's start with x to the power
Ma'am, just
2021
one
and
thing.
cos 2021x. This is an odd function, right? We just discussed why this is an odd function.
Ma'am, for the
On the,
odd function f of minus x is minus f of x, isn't it?
yeah, minus f of x. We've done the same here, right? It's minus f of x. Okay. So this is an odd function. This is an even function, right? Because if you do cos of minus x, you get cos of x. The sign gets absorbed, right? So cos x is an even function. Your x to the power 2021 is an odd function. And product of odd and even function is an odd function. Or you can try putting minus in this entire function. So it will be minus x to the power 2021 cos minus 2021x. So you will get x to the power minus x to the power 2021 cos of 2021x, which is the negative of the given function. That means
And ma'am, the product of odd and odd is an even function, na?
yeah, odd even function, even function, odd even or even odd gives you odd function.
Okay, ma'am.
Just a minute. If a even number is multiplied with an odd number, will it not give an even number?
We're not doing even odd numbers, we're doing even odd functions. This is
Okay.
an odd function and this is an even function. So product of odd and odd functions, we're talking about functions here. Product of odd and odd functions give you an even function. Product of even and even also gives you an even function only when you have opposite functions, odd function or even function. Then is when you get an odd function. So in the next one, this is 1, and then the next one is sine of 2021x, right? And we know that sine is an odd function because sine of minus x is minus sine of x. That means if this is your function and if I'll replace the x by minus x, this is gx. If I'll do g of minus x, I should be getting minus g of x, right? That means it's an odd function. Now x 2021 cos 2021x, this is odd and the other one is also odd. That means the sum is also odd, right? If I replace this entire, let's say this is your function 2021x. If this is your fx and I'll replace x by minus x, I'll be getting minus of fx, right? Should I do it here? We've already done it. Yeah,
Yes, ma'am. We have already done
everywhere.
that, ma'am. It's fine.
So it's minus f. If you take f of minus x, you get minus of fx. That means the integral of this entire thing should be 0, right? And if you have an even function, what happens here is when you have an odd function, that means from 0 to a, your function is fx. And from a to, I'm doing this so that you don't have to remember it. Otherwise, there'll be one more thing added to the list of things that you have to memorize. So this function is fx here and it's fx here. But you know that for the negative ones, if you'll put the negative ones, f of minus x is just the same as minus of fx, right? That means I can just simply take, this is the function fx. If I'll take it from 0 to a, then I'll have to take f of minus x, right? These two are equivalent functions. If I'll take f of minus x and I'll put values from 0 to a, it's the same as taking f of x and putting values from minus a to 0, right? If I'll put a minus a here, I'll get f of minus a. Or if I'll put an a here, I'll get an f of minus a. So aren't these two the same things?
Yes, ma'am.
These two are same. That's why you can just directly take this. But we know that it's an odd function, so it should be minus of fx. That means you're adding the integral of minus fx from 0 to a to the integral of fx from 0 to a. That means you're doing this fx from 0 to a and minus of fx from 0 to a, which is 0 only, right?
For the condition that a should be like 0 is the kind of a average point between minus a and a. Yes, ma'am.
If you have
That's why
a
it becomes cancelled.
and minus a, then obviously 0 is somewhere between a and minus a only,
No, ma'am,
unless your
middle,
a
middle.
is not 0. No, it doesn't have to be in the middle of.
No, to
So
get it
if you
cancelled,
have
ma'am.
2
To get it
points,
cancelled. To get it
yeah,
cancelled.
if you have 2 points, then obviously if you have minus a and a, 0 is obviously in the middle of these two, right? A is the middle point of minus a and a, right? In short, yes. A 0 is in the middle of a and minus a, that's why they get cancelled. Okay, and then the last topic is regarding the areas between functions. So if you have to find the area between, let's say, fx and gx, where let's say your fx is some function, this function, and your gx is this function, say. And you can clearly see that your fx, and you have to find the area from here to here, from point of intersection to point of intersection. So firstly, I hope you know how to find the point of intersection of two functions. How do we find the point of intersection of two functions?
We have to equate them, na, ma'am?
Yeah.
Yeah.
Equate them and then find the value of x. This will give you
Yes,
these
ma'am.
point of intersection. And then the area under f is this one, right? And you have to find this area. Just draw it properly. If you have this as fx and the other one as gx, this one as gx, and you have to find this area, then what you do is from here to here, you find the area of fx. So this will be this entire thing, right? This entire thing will be the area, and then you subtract the area, this area you subtract, the gx area. So if this is your fx, you take the area of fx from here to here. This will give you this entire thing. This is fx. Then the area under fx would give you this entire thing, right? And the area under gx would give you this entire thing. So if you subtract the area of gx from the area of fx, you would be getting the area of this area, right? Between fx and gx. So to find the area between fx and gx, you do fx minus gx integration from these points of intersections a and b. For example, let's just say you have to find the area between, or you have to find the area bounded by square root of x and 2 minus x and y equals to 0 line. So let's just plot these things first. So square root of x is this, right? This is your square root of x. Then for your 2 minus x, if you'll put y equals to 0, you'll get x equals to 2. So it's 2 comma 0. And if you put x equals to 0, you'll get y equals to 2. Be taking from 2 comma 0. This is 2 comma 0 point. And this is 0 comma 2. So you should be taking this thing. And now you have to find the area between these two and bounded by y equals to 0. Which line is y equals to 0? This is y equals to 0 line, right? X-axis is y equals to 0. That means you have to find this area. Area bounded by this line, this curve, and this curve. So it's this area.
Line is 2
So how
minus x is equal to y.
first you plot these two graphs. So root x is this one and 2 minus x is this one. We've just plotted these two curves. That's it. And then you see which area is being asked. So you are being asked the area bounded by root x, which is this line, this curve. Then 2 minus x, which is this line, and y equals to 0, which is this. Is that okay? So you have to find this
Yes,
area.
ma'am.
How do you find this area? We know that under this curve, if you have to find the area from here to here, you integrate this function from here to here, right? You integrate f function from a to b to find this area. So to find this area, what should I do? This area is bounded by this curve. So we divide it into two parts because till this part, this area is bounded by, let's call this area is bounded by root x and y equals to 0. And after this line, before the line, and after this line, you have your area bounded by y is equals to 2 minus x and y equals to 0. Right? Is this part clear? This line is what I'm talking about. Is this clear to everyone?
Yes, ma'am.
Okay. So what should we do? So we should find this point, right? X equals to a point we should find. And then we should, because the limits you put are of x, right? They are the limits that you put are of x, values of x, these, right? So first you integrate root x from 0 to this point a. And then you should integrate 2 minus x from a to this point. Where now what is this point and what is this point? How can we find these 2 points?
And that point would be the intersection of root x and 2 minus x. So we have to solve that.
This point or this point, x equals to a. So a is going to be the point of intersection of this and this line,
Yes, ma'am.
the x coordinate of the point of intersection. And then how do we find this one?
This is already 2, ma'am, because 2 minus x intersect x-axis at 2.
Yeah, so you put for x intercept, you put y equals to 0, you'll get x equals to 2. So this is 2 comma 0 point. And this you'll have to find by finding the point of intersection of these two curves, root x and 2 minus x. So equate these two, root x and 2 minus x, and find the value of x. That will be the value of a. Put that a here and find the solution. That's your answer. After that, it's just simple integration. The integration of this is this, and the integration of this is this.
Okay,
I
ma'am.
think we're done with the week 9 summary and
Yeah,
everything.
ma'am.
Is there
Mm, Ma'am, there is one thing. If f dash x, suppose f dash x is equal to 0, just ma'am, one thing. F dash x is equal to 0 and it is not local maxima, local minima, global maxima, or global minima, we can say that it's a saddle point, na? According to you.
don't go according to me, go according to
No,
the book.
ma'am, just
It
I'm
says,
asking, ma'am, just because
yeah,
you
then
said
you
it,
can say it's a saddle point. Yeah,
it's not
it
point
is
of
not a
inflection, but
local
it's a saddle
maxima.
point.
Whatever we have discussed the distinction between point of inflection and saddle point. Let's just not make that distinction here. And because everyone
Ma'am,
here
just I
says
was
that in,
asking if f dash x is equal to 0 and it's not local maxima, local minima, we can say that na, it's a saddle point. That is
you
what I
don't
want
say
to.
that in exam because that would be marked incorrect. You just say it, you
But
just take saddle point equals point of inflection for the exam.
according to you, it is na, ma'am. I'm just asking from your point of view in general.
What are you asking?
If f dash x is equal to 0 and it is not local minimal, not local
Yeah,
maximum,
then it's
then
a
it is a
saddle
saddle.
point. Yep.
Go by what's been said in the video because you will confuse yourself in the exam.
Let me just put a note here.
Ma'am,
If your book says point of, which I believe it does because a lot of people have confirmed it, if it says point of inflection is the same as saddle point, then please go by this only and you won't be asked saddle point separately.
Ma'am, there is one doubt in the just if you go up when you were discussing that Riemann integration multiplication. Yeah. On the yeah. More up, ma'am. Um, Oh yeah, on the right hand side, yeah. This right hand side, when you were discussing when we were having a right and left one, when you were doing the left one, I asked you, yeah. In a little down, ma'am, I guess. A little down. More down, ma'am. Yes, ma'am. Here you said it's 2n minus 1 according to 1 and n. Like I is 1 and n. Right
Yeah.
above. Yeah, ma'am. Ma'am, how did that come from? Like, how did you derive that 2n minus 1 upon n from this? I
Okay, if you've been given, even if you're not given this thing, this is something which is being given in the question. This is an activity question. This form is given there. But even if you're not given there, you would be given 0, 2 by n, 4 by n. So there's a pattern here, which is this is 2 into I by n. This is 2 into 1 by n. This is 2 into 2 by n. And this goes till 2 into n by n. And right before your 2 into n by n thing, you have, if you have 2 into n by n here, then what should be the one just before this one? We need that thing because we have the partitions here as 0, 2 by n, and we have to collect these points, right? For this interval, we have to consider this point. For the next
got it,
interval,
got it,
we have to consider
got it,
this
ma'am.
point. So we need the second last one. This is 2n by n. We need the point just before this. So this is 2n minus 1 by n.
Yeah, ma'am. Got it.
That's it.
And ma'am, the just above it, when you were saying it right, the area, yeah, ma'am, this one, the above. Here is this is the upper area, and this is the lower. What for? Yeah,
Yeah, lower Riemann sum.
yeah, and this is that was upper remarks area. So, what we like? How did we get there, ma'am? Like, from where did we? From where we got that?
When you have a function here, why are we finding Riemann sums? It's to find the area under this curve. So what we do is we divide, if you have to find the area from here to here, what we do is we divide into random intervals, right? And then what we select random points from here. So we take xi star here, and then we consider height as per this. So for this entire block, we consider the height as per the given point that's given in the question. But if it says upper Riemann sum, or if it says the right Riemann sum, right hand Riemann sum, that means you xi should be taken as this. For the left one, it should be taken as this one. And for the upper one, you should be taking the one where you achieve the maximum. So for the upper Riemann sum, you should be considering your xi star to be this. If the, in this particular case, for upper Riemann sum, you have to do xi minus 1. That means x1 minus x naught, and then fx1 star. So this one should be the maximum height of your function for the upper Riemann sum. For upper Riemann sum, this should be the maximum height of your function in this interval.
Ma'am, is there any
In the
connection
interval x0 to
between?
x1.
Ma'am, is there any
Sorry.
connection between right hand Riemann sum and upper Riemann sum? Like anything?
No, there's no connection as such.
Like
They're both
lower
Riemann sums.
Riemann?
That's the only connection.
I thought like what you derived it from below, like there is a connection between right hand Riemann sum and upper Riemann sum or lower Riemann
No,
sum.
no.
Is there any?
Upper Riemann sum is about the maximum height of the function, whereas your right Riemann sum, left Riemann sum are about these points.
Okay, okay. I thought there is some kind of a, when we derive it, I thought we use some kind of
There
technicalities
isn't.
here.
No.
Okay, ma'am.
There
Are
was
we done with this?
substitution, integration with substitution method that was explained in the video. Is that covered here?
No, it's not. Substitution is just, you don't have to do that. You won't need to, but let's do substitution too. Substitution is basically where you have, let's say, f g x. Formula wise, it's this only. And if you have g dash x here, dx. Then you substitute this thing as t because its derivative is present here, right? So if you substitute gx as t, then g dash x dx will be equals to dt, right? Or you can say dt by dx will be equal to g dash x, and then you can say dt will be equals to g dash x gx dx. So you can replace this g dash x dx by dt. So instead of this thing, you can put dt, and instead of gx, you can put t. So you will get ft dt. So it will turn into a simpler function then. And you have to change the limits as per this only. So if you have ab here, let's do a question here on this. Let's say you have sine root x dx from 0 to pi square by 4. Then you can substitute root x as t. So, and then you have to find the value of dx, right? You need to find dx in terms of dt. So this will be 1 by 2 root x, the derivative of this thing, dx equals dt. So your dx will be equals to 2 root x dt. But you want everything in terms of t. So you should replace this thing by 2t dt. And then this thing will give you sine. So in place of root x, you have t. In place of dx, this is dx, right? In place of dx, you have 2t dt. So this becomes 2t sine t dt. And then you have to change the limits too, because for x, your limits were from 0 to pi square by 4. But since you've taken t to be square root of x, that means square root of 0, square root of x, and square root of this thing. And you should be taking the limits from 0 to pi by 2. And then here you just have to use integration by parts. That's it. Is that okay? Consider this to be the u function, or you can just take u out. Consider this to be the u function, this to be the v function, and then solve it. Is that okay?
Yeah, thanks. Yeah.
Okay.
Can you
Or
just zoom
should we
in
do one more
this one? I
example
wanted
on
to,
this one? Yeah. What?
ma'am, can you just zoom in this? I just wanted to take a screenshot of this question. In, yeah, substitution one. Okay, ma'am, thank you.
Let's do one more on this. It's this x. This one's an easier one. So if you have this thing given, you can substitute x square plus 1 equals t. So you'll have 2x dx equals dt. So this thing will be square root of t, this replaced by t. And then dx is dt by 2x. So this is going to give you, and you have x dx is equals to, right? You don't have to do this. So x dx is equals to dt by 2. Replace x dx by dt by 2 and square root of x square plus 1 by square root of t. This will be it. And then you know how to integrate square root of t. That's all. Is that okay? If there are any other
Okay.
doubts, you can ask. Otherwise, we can end the session here.
Ma'am, when you said that that double differentiation is equal to 0, you said it is inconceivable. Those points are inconceivable. Like,
Yeah, inconclusive. The
yeah.
test is inconclusive. What
Can
about
you
that?
graphically tell us like those point where f dash x like
Can you
unconceivable
scroll up a
things?
little bit to show the substitution in which you wrote something? This whole
Yeah,
little
ma'am, if you can tell graphically those points, like how it is inconceivable, the double differentiable is zero.
little more up, ma'am. Up. I mean, oh, the substitution interval. You wrote something. Scroll down. Little bit. Yeah, here. I'm sorry. Yeah, thank
Is it
you.
done? Oh.
Yeah.
There are questions where your test becomes when you get f double dash x equals to 0. Let's say you have, even if you will take
To the
x
power.
cube, you will get the first derivative will be 3x square and then the second derivative will be 6x. So if you will put x equals, and if you're testing for x equals to 0, if you put x equals to 0 here, your double derivative, this is your double derivative, this will be 0. Right? So from this test, you can't conclude. We know that x equals to 0 is a point of inflection, but from here you can't conclude that it's the test fails here, right? We say that if your f double dash x not equals to 0, then your test fails. If this is greater than 0, then it's a point of local minima. If it's less than 0, it's the point of local maxima. And if it's 0, then your test fails. That means it's inconclusive. You can't conclude anything from here. Is that okay?
I think it's better if we extend my x to the power 4, man. Because x to the power 4, 0 is a local minimum. And double derivative is for critical
It
point.
fails there too. Yeah. In this
X to
one,
the power 4 also.
if you will take x to the power 4, it goes the same way. The double derivative will be 4x to the power 3, and then you'll have 12x squared. So this will be your double derivative. And if you put 0 here, you will get f double dash 0 equals to 0. So here, as per the test, the second derivative test, it fails here. So you can't conclude if x equals to 0 is a local maxima or a local minima. But we know that x to the power 4 graph looks like this. That means it has to be a point of local minima. So this is the point of local minima, but you can't conclude from here. Is that
But ma'am,
fine?
it should be in a way positive because it's a local minima. So f double dash x should be positive in a way.
Okay, for your double derivative test, it says if your f double dash x is greater than 0, then minima. If less than 0, then maxima. It doesn't, and if it's 0, then it could be maxima, minima, or it could be a saddle point. Now we don't know. We can't
But
conclude
ma'am,
anything.
here it is minima, na? Here it is minima.
But
It
that is
is
not
minima,
proved
but
by
this
the
doesn't
derivative
guarantee
test.
anything.
Huh?
It's not proved by the derivative test, which is minima, but it's not proved by the derivative
Use
test.
some other method.
Yeah, some of them.
Then you will have to move to some other method to show that this is a point of local. If this happens, then it's minima. But if it's a minima, that doesn't mean your f double dash x is greater than 0. It only this part is true. The forward part is true. The backward part is not always true. Same goes here. This implies local maxima, but the converse is not true. Is that okay? If there are any other doubts, I don't think there are, and it's already half hour past, so we can end the session here, I guess.
Thank you, man.
Bye, everyone.
Thank you, ma'am.